Deploying machine learning models in production is often a complex, manual, and error-prone process. Traditional software development cycles benefit immensely from continuous integration and continuous delivery, known as CI/CD. But how do we adapt these proven principles to the unique demands of machine learning? The answer lies in establishing robust, automated CI/CD pipelines specifically designed for ML workflows. This approach ensures not only faster time to market for new models but also greater reliability and maintainability. It transforms the chaotic journey from experimentation to production into a streamlined, repeatable process, essential for scalable AI initiatives. At its core, CI/CD for machine learning extends the familiar concepts of continuous integration and continuous delivery to encompass the entire ML lifecycle. This means automating the steps involved in developing, testing, packaging, and deploying machine learning models, along with their associated code, data, and infrastructure. Unlike traditional software, ML systems involve not just code, but also data and models as first-class citizens. Therefore, our CI/CD pipelines must account for data versioning, model retraining, and performance monitoring, integrating these elements seamlessly into the automation framework. Continuous integration for machine learning begins with robust version control for all assets, code, data, and models. Every code change, feature engineering script, or model definition should be committed to a central repository. Upon each commit, an automated system triggers a series of checks. This includes compiling code, running unit tests, and verifying data schema integrity. The goal is to detect and address integration issues early, preventing costly problems downstream. It fosters a culture of frequent commits and rapid feedback, ensuring the master branch is always in a deployable state. Continuous delivery for machine learning focuses on automating the release process. Once a model and its code pass CI, they are prepared for deployment. This involves packaging the model, its dependencies, and inference code into a deployable artifact, often a Docker image. Automated pipelines then deploy this artifact to various environments: development, staging, and production. The aim is to make deployments frequent, predictable, and low risk. This might include deploying to A/B testing frameworks or shadow deployments, gathering performance metrics before a full rollout. A critical distinction in ML CI/CD is the emphasis on data. Data is not static, it evolves, and so must our approach to managing it. Data versioning tools become indispensable, allowing us to track changes in datasets, link models to the specific data versions they were trained on, and reproduce experiments. This ensures data provenance and model reproducibility. Good data management also includes automated data validation checks within the pipeline, ensuring that new data adheres to expected schemas and distributions, preventing subtle data quality issues from impacting model performance. Testing in ML pipelines extends beyond traditional software tests. For the code itself, we employ standard unit tests to verify individual functions, like data preprocessing steps or custom model layers. Integration tests confirm that different components, such as feature stores and inference services, work together correctly. Functional tests simulate end-to-end scenarios, ensuring the entire ML application behaves as expected. These tests are automatically executed within the CI pipeline, providing immediate feedback on code quality and correctness. Beyond code, models themselves require rigorous testing. This includes performance metrics testing, comparing a new model's accuracy, precision, or recall against a baseline or a previous version. Fairness testing checks for bias across different demographic groups. Robustness testing evaluates how the model performs under adversarial conditions or with noisy inputs. Data drift detection monitors if the new data distribution significantly differs from the training data. These automated tests are crucial for ensuring model quality and ethical deployment before reaching production. The build phase in ML CI/CD involves creating deployable artifacts. This typically includes packaging the trained model, its serialized weights, the inference code, and all necessary dependencies into a container image, such as a Docker image. This container encapsulates the entire execution environment, ensuring consistency across different deployment targets. Metadata about the model, including its version, training data, and performance metrics, is also stored and linked to the artifact, enabling easy tracking and rollback if necessary. Automated deployment in ML often utilizes sophisticated strategies to minimize risk. Canary deployments involve rolling out a new model to a small subset of users or traffic, monitoring its performance intently before a wider release. Blue/green deployments maintain two identical production environments, one active blue and one inactive green. The new model is deployed to the green environment, tested, and then traffic is switched over, allowing for instant rollback if issues arise. These strategies ensure minimal disruption and rapid recovery. Infrastructure as code, or IAC, is fundamental for repeatable and scalable ML CI/CD. By defining infrastructure, such as compute clusters, data storage, and network configurations through version-controlled code, we can provision and manage environments consistently. Tools like Terraform or Kubernetes manifests enable automated setup of training and serving infrastructure. This eliminates manual configuration errors, improves reproducibility of environments, and allows for rapid scaling of ML workloads across different stages of the pipeline. Post-deployment, continuous monitoring and observability are paramount. This involves tracking model performance metrics such as prediction accuracy, latency, and resource utilization in real time. It also includes monitoring for data drift, concept drift, and unexpected model behavior. Dashboards and alerts notify teams of anomalies or degradation, allowing for prompt intervention. This feedback loop is vital for triggering automated retraining pipelines or rolling back to previous model versions, ensuring sustained model quality in production. Numerous tools facilitate MLOps CI/CD pipelines. Version control systems like Git are standard. For data versioning, DVC or Pachyderm are popular. CI/CD orchestrators include Jenkins, GitLab CI, GitHub Actions, and Azure DevOps. ML-specific platforms like MLflow assist with experiment tracking, model registry, and deployment. Kubeflow provides a platform for deploying and managing ML workflows on Kubernetes. Together, these tools form a powerful ecosystem for automating the entire machine learning lifecycle. Adopting CI/CD in ML requires certain best practices. Foster collaboration between data scientists, ML engineers, and operations teams. Emphasize reproducibility by versioning everything: code, data, models, and environments. Implement comprehensive automated testing at every stage. Prioritize security throughout the pipeline, from data access to model deployment. Finally, start small, iterate, and continuously refine your pipelines based on feedback and evolving requirements. Gradual adoption leads to sustainable success. Automating ML with CI/CD pipelines is no longer a luxury but a necessity for organizations leveraging AI at scale. By adapting continuous integration and continuous delivery principles, we can build robust, repeatable, and reliable processes for developing, testing, and deploying machine learning models. This not only accelerates innovation and reduces operational burden but also enhances trust in AI systems by ensuring their quality and ethical performance. Embracing MLOps is the future of bringing intelligence into production.